Hello everyone. The title of our project is Channel Selection Mechanism for IEEE 802.15.4 in Contiki operating system. Currently, Contiki does not have a mechanism in its existing protocol stack for dynamic channel selection. Nodes are arbitrarily assigned a fixed channel for transmission instead of choosing optimal one. This makes it difficult to use Contiki in high interference environments. Our project focuses on finding an optimal solution for channel selection mechanism by adding channel measurement parameters and a management block to the existing protocol stack of Contiki. This block will measure the interference level of the entire channel in predefined periods, and based on the results, it selects the best channel for network communication. We use Kuja simulator to simulate our network and log its performance. The IEEE 802.15.4 operates on 3 unlicensed frequency bands, that's 27 channels in total. It provides data rate up to 250 kbps. In 868.3 MHz, it works on one channel, channel 0. In 902 MHz, it works on 10 channels, channels 1 to 10. In 2.4 GHz, it works on 16 channels, channel 11 to 26. Contiki operates on these 16 channels. When the network is established, one of the 16 channels is chosen randomly for communication. If that channel is under interference by any other Wi-Fi signals, then the performance of the network is affected. We try to eliminate this problem by designing a channel selection mechanism so that Contiki can scan and find the best available channel for communication. So why do we need channel selection mechanism? The IEEE 802.15.4 uses the license-free ISM band for communication. At present, wireless LAN, Bluetooth, Zigbee networks are competitors in the 2.4 GHz band of the ISM band. In future, we can expect further overlaps as ISM band is going to be the host of numerous technologies. As a matter of fact, interference is unavoidable on ISM band, and appropriate mechanism need to be devised to ensure feasible coexistence among the technologies. From the literature surveys, we concluded that Wi-Fi is one of the main interference sources, and hence we focus our channel selection mechanism to avoid interference from Wi-Fi signals. In our project, we have used the following 3 scanning mechanisms, namely linear scanning, predictive scanning, and Wi-Fi prioritized scanning. In linear scanning algorithm, all the channels are scanned linearly. First channel 11 is scanned, and if found busy, the subsequent channel 12 is scanned, and so on. If a channel without interference is detected, that channel is chosen for communication. If interference is detected in all the channels with the lowest RSSI value is selected. In general, if say channel 12 is under interference, there is a high probability that channel 11 and 13 are also under interference. So in predictive scanning, we scan the channel in hops. First we scan the 4 hop channels. If these channels are found to be busy, then we scan the 2 hop channels, and then the remaining channels are scanned. This decreases the channel scanning time efficiently when compared to linear scanning. In Wi-Fi prioritized scanning, we skip the channels in which Wi-Fi operates. Wi-Fi communication takes place on predefined channels as shown by the black circles as channel 1, channel 2 and 3. So we give priority to channels which are not under the influence of Wi-Fi. We start scanning directly from channel 15 and then channel 20 and 25, 26. If these channels are found to be busy, then we scan the 2 consecutive channels from each Wi-Fi band. This ensures us to grab the next free channel immediately if the interference is from Wi-Fi or even from other sources. We can even extend this scanning mechanism for overlapped Wi-Fi bands. So before we present the simulation, we would like to talk about Contiki and how communication in Contiki MAC takes place. Contiki is an open source operating system for wireless sensor networks and Internet of Things. It supports low power wireless communication standards such as 6LoWPAN and RPL. The figure here shows the net stack of Contiki. It's divided into 4 layers: the network layer, MAC layer, RDC layer, and the radio layer. Contiki supports several MAC layers like Contiki MAC, Null MAC, YMAC, etc. The figure also shows the different protocols used in different layers. For our project, we chose Contiki MAC protocol. We choose Contiki MAC protocol because it's highly power efficient compared to other MAC protocols. Contiki MAC uses power efficient wake-up mechanisms, fast sleep optimization techniques which allow receivers to quickly detect false positive wake-ups from spurious noise levels. Contiki also uses phase lock optimization technique which syncs the sender with receiver's wake-up time, thereby making it more power efficient. In Contiki MAC, a receiver keeps its radio off most of the time and checks the channel periodically for any incoming packets. This is referred to as clear channel assessment. When receiver senses any radio activity, it keeps the radio on while receiving the packet. When sender wants to send a unicast packet to receiver, it checks the radio medium for any nearby radio transmissions, thereby trying to avoid collisions. Since sender does not know whether receiver is awake, it repeatedly sends the intended packet in strobes until it receives an acknowledgement from the receiver. A sender can remember the relative time in the wake-up cycle of receiving an acknowledgement from the receiver. This way, sender does not need to strobe for the whole wake-up period to send a packet. Instead, it can schedule a packet to be transmitted shortly before receiver's expected wake-up time. This phase optimization technique of Contiki decreases sending transmission costs. When a sender wants to send a broadcast packet to all the neighbors, it checks the radio medium for any nearby radio transmissions. Then it sends the packet repeatedly for a full wake-up period. This maximizes the possibility of broadcast reception. Contiki MAC defines certain timing requirements for ensuring correct behavior with duty cycling so that no incoming packets are missed. On wake-up, Contiki MAC performs 2 consecutive CCAs. If one of the CCAs is negative, it means an activity is detected and the radio is kept on for a longer period to receive a potential packet. When a packet is received correctly, an acknowledgement is sent. To ensure that a packet is not missed, it should be long enough not to fall between the 2 CCAs. Therefore, the minimum packet duration should be bigger than the time taken by 2 CCAs and the time between the 2 CCAs as shown in the figure. Also, the time between data strobes should be enough to receive an acknowledgement.
The design of a dynamic channel selection mechanism should cater to the shown requirements. Generally, it is desired that the overheads introduced due to this mechanism, such as power and latency, should pay for themselves in the longer run by the increase in performance of the network. The entire network should migrate to a new channel only if the interference is detected over a period of time. Over a period of time is important because that allows us to distinguish between burst activity and sustained interference over a period of time. This makes sure that channel switching does not take place too frequently or ignores substantive interference. The channel switch time, that is the time elapsed between the instance when interference is detected and when the channel switch takes place, should be as minimum as possible. Finally, the proposed mechanism should be compatible with the existing protocols. The mechanism of communication between PAN and nodes is explained next. A mesh topology is chosen in the design of our network. A PAN coordinator is the node which is responsible to carry out all the management activities in the network which are related to channel scanning and switching. It is also responsible for the creation of PAN network. A node which wants to join the network negotiates with the PAN coordinator to see if it can join the network. It will broadcast a request to join the network. Then the PAN coordinator will take a decision to either induct or reject the node. If it decides to induct the node, it will send a join request to the node. Then a connection is said to be established between them. All the other nodes follow the same procedure to join the network. After joining the network, the nodes perform a neighbor discovery and discover its single hop neighbors. When a new PAN coordinator is formed in the network, it will broadcast requests to join its newly formed PAN network. These requests may reach some of the nodes which are already present in a PAN network. Then these nodes will be in a dilemma whether to be under its old PAN network or to join the new PAN network. The nodes resolve this dilemma intelligently by taking into account RSSI values. The PAN network has been designed so that all the nodes within the PAN network can reach the PAN, one hop. The nodes can also reach their neighboring nodes within the PAN network. To ensure that the creation of these PAN networks do not disturb the existing communication architecture, it is allowed for the nodes present outside of a PAN network to communicate with the nodes present inside the PAN network, if they are in range.
Now we simulate our network and show how the channel switching takes place when there is interference present in the communication channel. For all the simulations, we are using Sky mode. We have three types of simulation setups. In this first simulation, we simulate our network design. As you can see, we have network with PAN coordinator and three network nodes. We also have a disturber node which can generate interference at specified channels. We start the network at channel 26. When we start the network, the nodes will join the nearby PAN network. It will find its neighbors and create a routing table, and it starts communication. As we can see, the red circles here represent the radio activity and arrows represent the communication. Now we create interference in the current channel. We can see that when the disturber node reaches near the vicinity of the network, the communication between the nodes is affected. In the timeline, the red marks denote the collision in the communication. This interference is reported to the PAN coordinator by the interfered nodes. The PAN coordinator starts the channel selecting process and finds the next free channel or less interfered channel. The PAN coordinator communicates the selected channel to nodes and switches the network to that channel. As we can see, now the network is operating on channel number 11. So the communication that was affected due to the presence of interference has been overcome by switching the network to channel 11. In this simulation, we demonstrate the different channel selection mechanisms. First, we simulate the linear scanning mechanism. We have the same network like the previous one, along with 5 static interference nodes, which introduces interference in the channels 11 to 15. We have another mobile disturber node, which will introduce interference in the current channel. Now we start the network. The nodes join the network and the connection is established. We introduce the mobile disturber node to our current channel number 26. When the mobile disturber node reaches the vicinity of the network gets affected and the PAN starts scanning for the channels. We see the PAN coordinator scans for all the channels from 11 to 15 and finds them with interference. The threshold value of RSSI is set to minus 45 dB. We see channels 11 to 15 have higher RSSI values. When PAN scans channel 16, it finds RSI value to be minus 45 dB and selects it for communication. Now the network switches to channel 16, which is free of interference. Similarly, we carry out the Wi-Fi prioritized scanning mechanism. The process of creating the interference is the same. Here we introduce interference on nodes 15, 20, 25 and 26. As explained before, we scan the non-Wi-Fi interfered nodes in this mechanism. We can see in the results, the PAN scans 15, 20, 25, 26 and finds them with high RSSI values and eventually switches the network to channel 11, which has RSSI value of minus 45 dB. This was Wi-Fi prioritized scanning. Now similarly, we carry out the predictive scanning mechanism. In this mechanism, as explained before, we scan channels in hops. So we introduce interference in channels 11, 15, 19 and 23. The pan first scans the 4-hub channels. These channels are found to have higher RSSI values. The pan now scans 2-hub channels, and channel 12 is scanned next and found to have lower RSSI value, and the network is switched to channel number 12. This was predictive scanning mechanism. We are using PowerTrace plugin of Kuja to analyze node performance. It shows the power dissipated at the different modules. As we can see in the Mote output window, for every 100 millisecond, it will give a trace of all the power dissipations.
The channel switch time for various channel switching mechanisms is tabulated here. Three network types are considered here. Network type 1 means that there are two nodes along with the PAN coordinator. Network type 3 means that there are three nodes along with the PAN coordinator. Interference scenarios types specify the worst case scenario for one type of channel scanning mechanism and shows how better the remaining two mechanisms perform over this mechanism. This table tabulates the number of received packets throughout the entire network and the calculated value of throughput when the simulation is run for a specified amount of time using the three kinds of scanning mechanisms. It can be seen from the previous tables that the performance of three types of scanning mechanisms are highly subjective to the manner of interference. Linear scan can be deployed in situations where the source of interference is either ZigBee or other IEEE 802.15.4 networks. Predictive scanning and Wi-Fi prioritized scanning mechanisms score over linear scan mechanisms when the source of interference is Wi-Fi.